All right, if we can prove that a whole bunch of scores creates a normal distribution, it's huge. So this is about predicting the future. There's going to be, what, about 50 million people that vote for president? They're doing these polls that are predicting who's going to win the election. I don't know, let's say 50 million people vote. How many people would you want to ask to determine, so you'd be happy and you think you've got the winner of the election? Let's say you had to bet $1,000 on it. So there's 50 million people that are going to vote. You're putting $1,000 on what you come up with. How many of those 50 million do you want to talk to so that you're pretty darn sure of your results? 10%? 5 million? Okay. Last period someone said 1 million. I bet I'm going to ask 1 million. They're polling. When they put these polls in the newspaper and on television, they're staking their reputation. They've got the winner. They're asking about 1,500 people. Out of the 50 million people voting, they're only asking 1,500 people to figure out who's going to win. And that's all they need to ask. In fact, you're going to learn a magic number in statistics, and that magic number is, hey, if you just ask this many, you can be pretty pretty sure of the answer you get. The magic number is 30. So this concept of a normal distribution is what allows us only to ask 1,500, or maybe only ask 30. Okay, but we have to be able to sniff out, hey, I got a bunch of numbers here. Are these closely, do these closely resemble a normal distribution? And one way to do it, we've already talked about it before, is take a look at the graph. Take a look at the histogram and see what's up. Now, you don't have these numbers in your calculator, but we can take a look at a histogram and come up with a pretty good idea as to whether the data is closely resembles a normal curve. This was last year's test results. So what do we need to say we have a normal distribution or not? Is the data unimodal? Yeah, got one big hump. Symmetric? A little bit less skewed here. Okay, it could be a problem. Does it have medium tails? Remember, this is the one we went and actually did. This side was okay, wasn't it, when we did that 68, 95, 99.7 test? And this side was a little bit cramped inside of here. So visually looking at it, we'd say, we're not real sure. Now, another way to determine whether you have a normal distribution or not is to go ahead and do this 68, 95, 99.7 rule. We did it in class. Remember, we found one standard deviation away both ways, and we counted how many scores were in there, and we want it to be around 68%. And I think that data actually came out to like 75% here, right? This was about 97, and this was all of them. So we can check those three places out and see if the data is somewhat normal from those. By the way, I don't know if I talked about it. This has another fancy name. I think I gave you a crazy Chevychev's thing last time. It's actually called the empirical rule as well. So whenever you hear the empirical rule, they're talking about this thing. You're going to do this on your homework tonight. I'm going to give you a bunch of scores. I want you to go through exactly what we did in class the other day. I want you to find one standard deviation away, find out the percent of scores that are in there. Go 2 standard deviations away, and so on.
Taking notes.
I know, you're taking it. Now the third way, and this is the way you're going to love, and this is the way you're going to do it from this point on, is to actually make a graph of the data points, and you'll be able to see from that graph much better than this one as to whether the data is closely resembled by a normal curve or not. And it's called a normal probability plot. Now here's the deal. This is how this works. You put a bunch of numbers in your calculator. Let's say you put 50 numbers in your calculator. Your calculator says, okay, you got 50 numbers in here. I know what the perfect z-scores would be for 50 numbers. I know the lowest number should be negative 2.73. And the next lowest one should be negative 2.5 or whatever. It gives the absolute perfect z-scores. In fact, 68% of them are going to be between negative 1 and positive 1, right? 68% of the scores within one standard deviation from the mean. Okay. Half of them are going to be positive, half of them are going to be negative. Your calculator knows the perfect z-scores. But then it compares them to what the actual test scores were. And it graphs them on an XY plane. Okay? Let me show you what it looks like. So the normal probability plot, go to stat plot, and it's this guy. If those points come out to a perfect straight line, then your data can be closely approximated by a normal curve. If your actual data matches up with the right z-score, the points will come out in a perfect straight line. So let's do your class here. Now it's going to ask you a couple of questions here. First of all, where's your data at? And then it's going to say, hey, where do you want the actual test scores? Okay, it can be an X or a Y. This could be perfect z-score. You can put the actual scores here. Okay, so just understand you might see it either way. Okay, and what kind of marks do you want to make for it? All right, let's make this graph. Now remember, we're looking for a perfect straight line. I just learned how to this trace key. I didn't even know it existed. I found out today. Right there. Boom! Look at that. All right, at that point, the lowest test score was a 35, right? So the x-coordinate is 35. Now, I think there were 33 test scores. So the absolute perfect z-score, if you have 33 scores, is negative 2.1. Your calculator figures that out. You're never going to have to figure it out. I have no idea how it does it. It just knows the perfect z-score, if you have 33 scores, is negative 2.16. Okay? So that's the point at that spot. If you keep going around, all the different test scores are here. All you need to focus on is the shape of this thing. You're looking for a perfect straight line. Do we have one here? Well, we're looking pretty good here in the meat of the data. Okay, but we got a little problem over here. The graph goes that way, right? Should be coming straight down, but it goes that way. We know what that means. This means, in this particular problem, the data was skewed left. Now, here's why. Let's keep this going down in a straight line. Straight line, straight line, straight line, straight line, straight line. So that point for that z-score should be right about here. U should be over here, which would keep you in the straight line. That's a score of 35. You should be up here around 42. That low score shouldn't have been 35. If this was a perfect normal curve, that last score would be around 42. So the 35 made the tail go longer that way, and it was skewed left. So you've got to not only know, hey, is it a normal curve or not? From this, you can tell me how it was skewed. So this guy, nice, 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 nice. The test score, this is test scores, right? You went too fast that way. Now let's look at the other side. If it was skewed right, you'd be going, 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 and it would go flying out this way. But we didn't, the maximum was right here, right? In fact, this guy is coming up this way. That means there were too many test scores bunched on the high side. Remember how that histogram on the high side didn't go out nice and normal out there? They all kind of bunched up over there. That's what you're seeing here. So, can this data be closely approximated by a normal curve? Not bad, but it's somewhat skewed left. And you're just looking for a straight line. It's a lot easier than trying to find unimodal and right tails and all that stuff. Let's take a look at your class. So your data is in L6. Ooh, okay. A lot wavier going on here, right? So you guys are less normal than the other class was. But notice what's going on here. Both here and here, I'm getting the same things. Now what happened there is on both ends, it should have gone out further, but it didn't. I'm saying, hey, you should have been over here, test score. You should have been way over here. Over here. No, over here, I'm sorry. If you stayed on this line, you'd be down here. The test score should have been down here to keep it in a normal curve. So both ends didn't go out as far as they should have gone. Okay, taking a look at your histogram.
I think you've seen this before.
Wow, boom. You should come out here. Right? But you all got bunched up here, which is good. It's on the high side. That's where you want to be bunched up. Down here, it should have come out further to make a nice, perfect normal distribution table. Okay? So, given a group of numbers now, you've got a graph that you can trust that's quick, when you can determine whether the data can be closely approximated by a normal curve, number one. But you also have to tell me if it was skewed and how it was skewed by looking at that line. That's a skill you have to have as well. Okay? So 3 ways to determine. Visually, least effective. This is a long time. You've got to do this problem tonight. You'll see it takes a while. And find the normal probability plot. That's what you're going to use, and you're going to be able to determine whether the data was closely approximated by a normal curve. How's it come about? Takes the actual score, compares it to the ideal z-score. You get a straight line, you've got a normal curve. Questions? Comments?